All right, ladies and gentlemen, so we are diving into the fourth part of 7.2. All right, and so in this video, our goal is to integrate with respects to y. All right, now we've done it a couple times, and we're in an application sense, and so let's kind of first talk off just why do we do it? Well, simply put, because it's sometimes easier to integrate with respect to the y's being the variables versus if it was x. And so it can be done at any time when you're focusing on area between enclosed curves, but you want to at sometimes just kind of understand that the boundaries of a region are just simply more easily described by a function in terms of y than sometimes by a function of x, right? And so think about what we did before. When we would find the area under the curve with respect to y, we did them kind of approximating our rectangles, right? And if you remember correctly, all those rectangles were vertical, right? So they were vertical. So now think about what the concept would be here. Now I'm in terms of x, how would we write our rectangles? Hopefully you understand that where I'm going with this is now that the rectangles would actually go in a vertical, or in a horizontal, plane of motion now. Interesting, interesting, interesting. And so I think the best way to kind of look into this is in a more of an application-based problem here. Just find the area of the propeller-shaped region enclosed by the curves. And so as you see here, I have x minus y cubed and x minus y. All right, this is our graph that I've gone ahead and graphed on the TI-84 for us. Now obviously I have this I have it graphed in terms of x. I had to solve for y and then graph it in terms of x. But really I want it in terms of y. So really what I'm seeing here is that the value x equals y cubed is our function, and then our other one, x equals y. Those are our two functions that we're going to be dealing with here. And so let's see if I can maybe see this a little bit. When we're trying to find the area under the two curves, take the greater curve and then subtract our lesser curve. Well, look what happens here. As I start to rotate this graph, let me get rid of these markings I have now. Ah, interesting. Now what actually becomes the greater curve that we're dealing with? Technically, the greater curve is our straight line, the red line, our x equals y graph that is in there. Super interesting stuff. I'm gonna go back and rotate it back, however, though, just so we can kind of visualize what it's going to look like for our limits and our bounds, though. And I'll rotate it back here in a sec as well. So let's take a look here. So normally it would be our integration of upper minus lower. And so really that's y minus y cubed. But what are our bounds going to be? Well, think about it. Now I'm going horizontal with things. So really it's from 0 to 1 for our intersection, and then you have 0 to -1 as another intersection point in there. So we've got the origin, -1, and 1 being our points here. So just kind of because we haven't really done this in a while, I'm going to go ahead and just say, hey, this is 0 to 1, and then multiply it by 2, right? Just using our properties. Now you can do it from -1 to 1, all right? I just wanted to switch it up a little bit here and go from 0 to 1, just multiply that by 2, and because it saves a little bit of time as well. But now check how easy this anti-differentiation is going to be. So now 2 y squared over 2 minus y to the 4th over 4, all evaluated from 0 to 1. So basically this becomes 2 times 1 over 2 minus 1 over 4, and then minus our 0 that's in there as well. And so kind of in doing so, obviously we're going to end up saying that we have our 1/2 times 1, and then our 1/4 times 1. This will end up giving us our 1/2 in the end. All right. So kind of interesting how it kind of all dives on into play here. So the value of this area is going to be a half when it's all said and done. But once again, notice how we had to focus on the change of direction. Now I rotate my graph around to kind of see the possibilities that are happening in this one now. All right. So very interesting problem to deal with. All right, ladies and gentlemen, take a look at this one again, and we're on to the next one.